Compliance, Bizria's compliance testing division. Hopefully today you'll find this informative as we look at ventilation systems in a little bit more detail. There are opportunities to ask questions, and if you would like to post those, I will respond to those after the webinar by email for you. And if we're ready, let's begin. Indoor air quality in buildings is closely linked, as we all know, to the health of its occupants. A study by the National Institute for Health and Welfare revealed that exposure to indoor air pollutants is linked to reduced life expectancy and burden of disease. 57% of the burden relates to cardiovascular, 23% to lung cancer and 12% to asthma, considering that the UK is amongst the highest in the world for asthma. The report suggested that the burden could be reduced by up to 38% by improving ventilation in property. Invisible risk has resulted in 1 in 5 homes suffering from mould and mildew, and it is the building regulations and standards that set out the minimum requirements meant to alleviate this, and this all comes under the heading that there shall be adequate means of ventilation provided for the people in the building. What we're going to look at today is the types of systems employed, the compliance outcomes that have been observed by both Bizria and various other bodies, basic considerations for ventilation systems, what happens when or if, and some of the documentation that can be provided to help alleviate these issues. So if we look at the systems first, building regulations look at 4 different types of systems. System 1 is intermittent extract with background ventilators, or most commonly called trickle ventilators. This is the most commonly used system, as it benefits from low-cost components and relatively short duct runs. It provides rapid extraction at the source of the pollutant. System 2, that we're not going to look at because it's so sparsely used, is passive stack ventilation, basically a tube from inside of the building to outside. System 3 is another commonly used system, so it's a continuous mechanical extract. So it continually extracts air from wet rooms, so kitchens, bathrooms, cloakrooms, utilities, etc. at a low rate, and it can also be boosted by either manual or automatic means as the pollutant level increases. System 4, similar to System 3, continually runs extracting from wet rooms, but it also supplies fresh air into habitable rooms, bedrooms, dining rooms, lounges, etc. Bizria in the last 4 years has visited approximately 160,000 new build dwellings, and this represents the makeup of ventilation systems in those dwellings. So as we can see, System 1 is the predominantly used system, ranging between 65 and 70% depending on which year you look at. Second is System 3, which accounts for around 1/4 of all installations, and we can split that up a little bit further by saying that the majority of System 3 installations are decentralized systems. So rather than having one central fan unit that is ducted to each wet room, there are individual fans like in System 1 located in each wet room. System 4 accounts for somewhere between 9 and 11% of total installations, and is obviously more prevalent in flats than houses. If we look at some of the outcomes of testing that have been performed by Bizria and other organisations, we see that for System 1 in 2016, just over 28% of everything that we tested failed to meet the minimum requirements for flow rates in dwellings. Interestingly, if we split that down further and look at clients that we worked for, it was the first time that we tested for them, this increases to 84%. So it shows that there are a lot of lessons that need to be learnt. The Zero Carbon Hub also conducted some research into System 3 and System 4 installations. They showed that 100%, that's 100% of dwellings failed to achieve the minimum trickle rates required, and 83% the boost rates required. And It's an even worse reading when we look at system 4. 100% of minimum flow rates and 100% of boost flow rates failed to achieve the required rates. But the installation isn't just about airflow rates. It also works around the provision of background ventilators, so how many trickle ventilators that we have in the room. And interestingly, it is quite common to have too many trickle ventilators. Basically what tends to happen is wherever we have a window we put a trickle ventilator on it, so we can be over ventilating the building. And considering that ventilation can account for up to a third of space heating costs, that isn't an insignificant impact. Quite often controls aren't marked. We see switches that look just like light switches but aren't clearly labelled to tell you what their function is. A very poor understanding of commissioning requirements. When the installers and commissioners were surveyed as to their practices, many of them hadn't commissioned the systems. They left manuals with homeowners so they could commission the systems themselves based on how loud or quiet the systems were running. And there was an incorrect provision of air transfer throughout the building also. Ventilation performance, we need to look beyond flow rates. We need to look beyond the size of the fan that we install. We need to look at the whole system, all the way from an air valve in a room to the extract terminal, including ducting, bends, etc., as all of these will apply resistance to the system that will affect performance and ultimately compliance. Every bend, every additional length of ducting will increase system resistance. A good design must calculate the system resistance and specify product based on that. Just an example of this is we have an installation where we have a a fan that is for a 15 litre a second application. So this would typically be a fan that could extract 23 or 24 litres a second of air in free air, so with nothing connected to it. We've installed it with 1.2 metres of ducting, and we've put two different types of terminal on the end of that ducting. The first being a 100mm grill, so quite commonly used. In that scenario, we measured the fan and it scored 17.4 litres a second, so in your 15 litre a second application that would be a pass. But when we change the terminal type to a tile vent, the resistance of that tile vent caused the fan to only extract 8.3 litres a second. So one small change made a significant difference. We also need to look at things that aren't necessarily considered to be part of the system in terms of inlet to outlet. So we need to look at things like the undercuts from doors. So fans need to be able to move air around the building, and they need to be able to draw that air or push that air from one place to another. So there needs to be significant undercut under the door. We need to have the right number of trickle ventilators in the right rooms. We don't want a trickle ventilator next to an extract fan, for instance, where short circuiting might be occurred. We said we need the right kind of controls suitable for the application. So for instance, in a cloakroom where moisture might not be the main pollutant, we need a manual control rather than an automatic one. We also need to look at ventilation in terms of air tightness of the dwelling as well. There are different ventilation strategies based on air tightness of the building, and these need to be taken into consideration. The success of an installation doesn't stop at design, and compliance can be put at risk if the designer does not follow the design. So we have a scenario here where the installer didn't route the ducting as suggested. So we can see on the diagram there the duct routes are straight up to the closest external wall, but the installer took the fans to a different wall. Okay? And this can have significant effects. The installation was still performed reasonably well. The bend off the spigot of the fan was smooth. The ducting was supported along its length. They used rigid ducting where it penetrated through the envelope of the building, so that one, it wouldn't be squashed, and secondly, it could be sealed around from an air tightness viewpoint. Okay, and we can see there are no sags in the ductwork that would collect any moisture. So they'd installed it pretty well. So we've got a 15 litre a second fan again. Because this is a sanitary accommodation, it only is required to extract 6 litres a second. But when we measured it, it's only extracting 5.6 litres a second. So it's a fail. And that is purely down to the increased length of the duct run that was employed. But why did the installer do that? You may have noticed that the way in which it had been installed meant that the ducting didn't need to pass through any joists, so that was obviously easier for the installer. But in this case, that wasn't the main concern. When the system had been designed, it hadn't been designed by looking at what other services were going to be present in that void. And as we can see here, there are a significant number of other services in that void, and it was therefore impossible for that duct to be routed through that space to the closest external wall. The installer did what they thought they could do and thought that what was the best scenario, but didn't understand the impacts of extending that duct run. Here we have another scenario where we've got a fan that's failing to do the duty, and when we look at the installation, we can see that first of all there's too much flexible ducting that's been used. It should be limited to 1.5 meters in length. We can see that there's too much ducting in respect that it's not been pulled taut, so we can keep pulling it out like some sort of magic trick. We can see that it's been compromised where it passes through next to other services, so we can see it's been crushed there as well. Another example of where a small change, a very, very minor change in the product that was used can have a significant effect. So on this installation, the specification was to use a 100mm grill, as can be seen on the left. In fact, that specific model of grill was to be used, but the installer didn't use that. He purchased a 100mm grill, so what could be seen as exactly the same thing, but it had a fly mesh in it. Okay, that changed the fan performance. So when it was measured, the two fans that terminated in those types of grills measured 10.2 and 10.9 litres a second against a design of 15, so therefore failed. When the fly mesh was removed, we can see those are increased to 16.9 and 17.4 litres a second, and compliance was achieved. Similarly, we need to look at the way that we use the products that are designed into the system, and whether we can limit system resistance by perhaps changing what we're using. So we've got a scenario here where we've got a cooker hood in a kitchen. Flexible ducting has been used to connect the fan spigot to the outlet. It's been foamed around, presumably for some sort of air tightness measure, although it's not technically in the right place. That will have restricted the ducting, when we could have used a piece of rigid ducting and virtually eliminated any system resistance associated with it. Here we have a MVHR application, and I think it's quite obvious that the problem here is the amount of flexible ducting in use. I'm guessing the installer was being paid by the meter. And this is perhaps one of the most concerning things. What we've seen so far in the scenarios that we've looked at is we've seen that poor installation has resulted in failure. With a centralized system where you have the ability to vary fan speed and therefore flow rates, what we tend to find is that in this type of installation, rather than go back and rectify the installation and remove ducting and design it better, the fan speed gets increased. They have sufficient power to overcome a lot of the resistance, so you can achieve the required flow rates, but the fan is running at a faster rate. It is therefore noisier and less efficient, And it's in this type of scenario that these units are normally isolated by the homeowner because of the noise from the system. Okay, so just because you've got the right flow rates, it doesn't mean that the install is working effectively and properly. Air tightness testing was introduced into the building regulations in 2006, and since the introduction of air tightness testing levels have reduced significantly in buildings. So pre the introduction in 2006, a BRE study showed that the average air permeability, the air tightness level of a building, was around 12. Since that point, the average has now dropped to just under 5, so a significant reduction in the air tightness levels. And one of the concerns with that is that we're not getting advantageous ventilation, so we need to ensure that our ventilation systems are working properly and in compliance. So in 2010, there was an introduction into the building regulations to ensure that systems were measured, the airflow rates recorded, and that information was lodged with building control or local authority. One of the things that it states is that the equipment that's used to undertake those measurements should have been calibrated within the previous 12 months at a UCAS accredited laboratory. It should be calibrated as a system, so if you have an instrument that's then got an air capture hood with it, those are calibrated together, and it must be achieving an accuracy of plus or minus 5%. Our research shows that less than 10% of test equipment that is in use at the moment has been or has ever been calibrated. Okay, so it's just not happening. The equipment that we use can have a significant effect on the measurements that we take. So this video just highlights the effects of different types of equipment. So what we have here is we have a 60 litre a second fan. We're going to measure it with this piece of equipment, which is called a powered flow hood. Quite basic installation, just ducted to a terminal, and we can see that we're going to achieve the 60 litres a second that we want, or we think we're going to achieve the 60 litres a second that we want. So the final measured value is 60.5 litres a second. We would accept this as a pass. The most commonly used piece of equipment in use is what's called a vane anemometer, a rotating vane anemometer, and a hood assembly. So it's just a windmill that goes round, and we can see this device on the same fan, there's been no changes, is telling us that the flow rate through the system is 37.6 litres a second, so somewhat different from the 60.5 that we've seen previously. The second most common equipment used, again, is another form of rotating vane anemometer, just from a different manufacturer, slightly bigger hood. And again, we can see that this is telling us that the measured value is around 37.4. So we've got 60.5, 37.6 and 37.4. So my question is, which method measured the actual airflow through the fan at the time of measurement? Method A, method B, or both? And the answer is it's actually both. All those three pieces of equipment have all been calibrated. They've all got calibration certificates saying that they're within 5%, but they are affecting the fan performance. And we can demonstrate that by putting both bits of kit on the system, so one on the inlet and one on the outlet. And we can see now that the powered flow hood is reading the same as the other two, because the vane anemometers are impeding the fan performance. Okay. And just to reaffirm that, with the second piece of equipment, you'll see the same thing. So what we can say then really is that just because you've got an instrument that claims to be accurate, it doesn't necessarily mean that the measurement will be accurate. So you need to understand the effects of the instrumentation on the fans that you are using. So there are lots of these bits of kit out there. The main difference, apart from their functionality, is that the first piece of equipment that you see costs about £3,000. The other two pieces of equipment about £500. So you can see why they're selected for use. And as a result of that investigation, there are actually three methods that can be used to certify the performance of a system. So we have the unconditional method, the conditional method, and the minimum benchmark method. Now the unconditional method is straightforward. It uses a piece of equipment that either does not apply resistance to the system or corrects for it. So it's basically what you see is what you get. So the number on the instrument is what the flow rate actually is doing. There is the conditional method, which is used for pieces of equipment that do apply resistance, so like a vane anemometer that you've already seen. And what that relies on is having specific coefficients that are used for a particular type of instrument when used with a specific type of fan. You can apply those coefficients to your measurement to obtain the true airflow through the fan without resistance being applied to it. Those coefficients don't exist, so you can't actually use that. So what's become the common method of measurement is the minimum benchmark method. So what we did here is we looked at what the average effect was of a rotating vane and a hood on a fan to establish what might be deemed to be compliant. So for instance, we found that if you were using a rotating vane on a fan that was extracting 15 litres a second, that would typically display 12 litres a second, 24 for 30 and 35 for 60. Now what you need to bear in mind with this is that anything that's looking at an average will fail some systems that should pass, and it will pass some systems that should fail. The other thing to note is that this is only applicable for system 1, so intermittent extract fans, and it is only applicable for axial type fans. So most cook hoods, for instance, will probably be a centrifugal type fan, so you couldn't use the minimum benchmark method for that. Okay. Now, one of the things that we have to provide in terms of documentation after a test is a list of the airflows and information about the property, and that's the document that needs to be given to building control within 5 days of the test. So there's a document that is applicable for System 1 axial fans, which is this document here. It's an NHBC document. We can see it's got information about the plot, the type of equipment used, calibration information about the equipment, what method you were using, and then spaces for information regarding the fans and the airflow requirements and measured values. Likewise, in the Domestic Ventilation Compliance Guide, there's also a check sheet. This doesn't deal with the minimum benchmark method because this was produced before that method was introduced, but it does cover all the systems. So here we've got System 1, but there are other sheets for System 3 and 4, and we can record the room rates for each room, both design and actually measured. But there's no point filling out forms if there isn't somebody to check those forms and make sure they're accurate. So we've got an example of a form here. It's actually at somebody at Bizria bought a new house, and they asked for a copy of the fan performance certificate from the house builder, and they were very proud to say, we've got a certificate and here it is. But obviously nobody knew what it meant or had looked at it to review that it was right. So apart from the obvious things that we don't have an address, so we don't have a development on there, we don't know if this is plot 258 on this development or somewhere 600 miles down the road, there's some other information that we can glean for this. So we've got an anemometer there. It tells us it tells us the model of it, but that would have been used with a hood, but it doesn't tell us that it was used with a hood. It is good to see that it is within calibration, so it needs to be calibrated annually. So it was calibrated, so that's fine. I can tell because STD it normally means standard, so it was a standard calibration if you look at the certificate number, so it wasn't a UCAS calibration, and therefore the correct coefficients wouldn't have been used, so the equipment shouldn't have been used. This was a System 1 installation, and we can tell that by the type of form that was used. And we also know the type of equipment that had been used, and we know that that can't be used for a Method 1, but they've told us that it was a Method 1 test, so that's wrong. If we look at the results, although they've ticked Method 1, they're obviously using the minimum benchmark method, because they've said that the first 2 fans have scored 12, and they're obviously saying that it's okay because they put a tick in the pass-fail box. So they're obviously saying 12 is equal to 15 if you use that minimum benchmark method. Okay, but the cooker hood is a centrifugal fan, so you can't use method 3. So you needed to see 30 litres a second, but they've taken it as being 24, the minimum benchmark method, so they declared it to be compliant when it isn't. Now the interesting thing about this is that we actually went and tested this property, and in this scenario the cooker hood was actually doing significantly more than that, and actually so were the bathrooms, and the results had been made up. So look for things that don't look right. So if you've got fans that are all just appearing to pass, they're normally a wide variance in results that you'd expect to see because of the quality of the installation. So if you see consistently the things that are just passing, then perhaps you should question that. Now there's other sections of the Domestic Ventilation Compliance Guide that should be completed but aren't required to be lodged with building control. So this is really information around the property, more information about the installation itself, checking that there are the right controls, the right number of trickle ventilators, checking that there weren't any abnormal noises when the system started up, checking that there are undercuts underneath doors, etc. And we haven't seen any of these being completed because it's not a requirement to submit them. But I would strongly suggest that people do have these completed, just to make people think about things and get them to put their name to something that they have checked that all parts of the system, not just the flow rates, are compliant. So to summarise really, from a design viewpoint, everything must have a holistic approach. We need to have clear and detailed specifications all the way from the fan to the terminal. We need to make sure that we've got the right amount of background ventilators. Too many can be just as bad as too few. Ensure that the ventilation strategy works with the air tightness levels that are going to be achieved within the property. Once we know that we've got a good design, we need to ensure that the design is followed. Have the correct products been used? Has it been installed in the correct layout? Are the controls the correct controls? Make sure that products haven't been supplemented for a different type or a cheaper design. Get the installer to complete the installation records. And once we've done that, we can review that certification, checking that we've got realistic values, all the values are complete, some simple checks just to make sure that everything looks to be above board. Make sure the equipment is within calibration. And finally, if we implement procedures to cover everything from inception to delivery, then there's no doubt that we can improve compliance and deliver functioning installations. Thank you for your time this morning, and as previously stated, I'll respond to any questions that you may have later on today.